Suppose I have some charge Q here and another charge Q here. I'll call this Q1 and Q2. Now, for the sake of this, we will just assume that they're both positive, that this will be repelled. This is going to move in that direction because of the electric force. We're going to use this as sort of our center, looking at the forces acting on this. Go back to the work-energy relationships. I know that the total work is equal to the change in kinetic energy. The non-conservative work is equal to the change in energy, and the conservative work is equal to the negative change in potential energy. What we're going to do here is derive the formula for potential energy. So, since the electric force is a conservative force, this is the one we care about. And so this force is going to be applied at some initial radius to some final radius. I know that work is equal to the integral of f dot dx, ds, dr, whatever letter you happen to be using. So conservative work means that's a conservative force. So we're integrating from r initial to r final of our force dot dx. Well, the force is in the same direction as the movement here. And so therefore, we can sort of get rid of the dot product here, and this just becomes fc dx. Or why don't we go ahead and make it dr, since I'm using r here. And so if this is from some initial to final radius of k q1 q2 over r squared dr. Well, I can pull my constants out, q1, q2, r1, r initial to r final of r to the negative 2 dr, which is negative k q1 q2 times 1 over r from r initial to r final, which is negative k q1 q2 times 1 over r final minus 1 over r initial, which is negative k q1 q2 over r final plus k q1 q2 over r initial. Now, that should be equal to the negative change in potential energy, which is negative of u final minus u initial, because change is always final minus initial. The negative sign distributes, and we get negative u final plus u initial. And we have a parallel here. So if the potential energy is equal to k q1 q2 over r, then this works. But do recognize that there are actually an infinite number of formulas that work, because we can always add a constant. So if I say plus 3, for example, then I would plug in our information here to plug in r final plus 3, and then the minus sign would distribute. And then I'd have a plus 3 here, so the negative 3 and the positive 3 would cancel out. And so any constant that we tack on does not change it. However, when stating the formula for electric potential energy, we do need to be careful here. So we generally say if u equals 0 when if r equals infinity, then it's equal to k q1 q2 over r. But so u equals 0 if r is infinitely large. Because we can set our potential energy equal to 0 anywhere. What really matters when dealing with energy is typically the change in potential, not the actual value itself. So be careful about that. I have asked test questions where this assumption is not made. So just watch out for that. And put a little subscript e. Notice that this is not a vector, as energy is not. It springs from vectors, but the vectors, we do a dot product, which is a scalar product, so the vector goes away.